Okay, in lesson 1, or in the review lesson in this unit, we went over some review of how to work with rational functions. So what we're going to do now is we are going to start looking at what these rational functions look like when we graph them. So just a reminder, a rational function is any function that's in the form y equals p of x over q of x. So a polynomial over another polynomial where the bottom cannot be 0. Okay, so those are our non-permissible values, so that still remains. Now, in these graphs, you graphed these a little bit in grade 11, and you should remember, hopefully, the idea of an asymptote. But now, we also have in these graphs something called points of discontinuity, or, more simply put, we can call them a hole. So you can actually have a hole in your graph at a very particular point. Now, to determine what these characteristics are and whether we have a hole or an asymptote as part of the graph, we have to look at the factored form of our rational function. So, if we look at, I've got a few examples here. This first example, there's no common factors between the top and the bottom. Because there's no common factors here, it means that we would just have a vertical asymptote where the bottom is equal to 0. So wherever the bottom is equal to 0, remember this means that x cannot be negative 9. That results in an asymptote in our graph. So anywhere that x equals 9, the graph does not exist. Now, the difference is that if you look at this second example, we've got x cannot be negative 4 as our non-permissible value on the bottom. But you'll notice that we have a common factor up top. So this x plus 4 is a factor on top and bottom. So when we simplify this polynomial function, excuse me, those factors are going to cancel. Now, because those factors are going to cancel out, in this case, this creates a hole in the graph. And this hole will only exist at x equals negative 4. And I'll show you in a little bit how to find the y value of that point. So this, because those factors cancel out, gives us 1 point of discontinuity instead of an asymptote at that non-permissible value. Now, it is possible to have both of these scenarios in a function. So if you look at this last one, our non-permissible values are x cannot be negative 2 and x cannot be 1. And you'll see that this factor of x plus 2 is common on the top and bottom. So that would result in a hole in the graph. But this x cannot be 1 would result in an asymptote. So this graph would have both a hole and an asymptote in it. Now, in this lesson, we're not going to actually get to graphing these sort of like we did with polynomials. We're going to start by just looking at these rational functions and trying to determine their characteristics. In the next lesson, we'll actually take all of those characteristics and graph them. So in example 1, what I've asked is for you to use the equation to determine whether the graph will have vertical asymptotes or holes in it. So the first thing that you always want to do is you always want to begin by factoring everything. So you'll notice in this first example, the top can't be factored, but the bottom could be factored. Now this bottom, remember, could also be factored to this. That might look a little bit more familiar to you. These are the same. Okay, so in this function, we've got x cannot be 3 and x cannot be negative 3. And there's no common factor on the top and bottom, so that means there's vertical asymptotes at x equals 3 and x equals negative 3. If we look at example B, I factored the top, so the top trinomial factors to x plus 1 times x minus 2, and on the bottom we just have x plus 1. Now, because this factor is common, this means there is a hole in the graph at x equals negative 1. In example C, I've got x minus 5, x plus 5, a difference of squares when I factor the top, And again, I have a common factor top and bottom, so there would be a whole at x equals -5. And on example D, on the top, all that I can factor out is this common factor of 2, and I get x plus 2, x minus 2. So there's no common factor. This just means that there's a vertical asymptote at the non-permissible value of x equals 2. So that's how we deal with vertical asymptotes and holes in the graph. On the next page, we're going to talk a little bit about horizontal asymptotes. So remember, horizontal asymptotes occur when there's a value of y that cannot exist. And the thing to remember about horizontal asymptotes is that, or really any asymptote, is that they show a trend. So remember, graphs always go towards asymptotes. So when we're talking about horizontal, now I've also included this oblique asymptote here. You can just cross that out. We're not going to worry about oblique asymptotes. Those are diagonal asymptotes. We're just going to worry about horizontal. So what you want to remember when you're dealing with these functions is that because you're working with a fraction, if you know what's happening as you increase or decrease your x values, it's going to give you an idea of what's happening on your graph. So if we look at a function like this, f of x over g of x, which is a polynomial function, those two functions, if we knew the degree of the top and the degree of the bottom, we can actually tell a lot about the graph. So if you think about, for example, if you had x over x squared. Okay, so if you had x over x squared, as you put x values in here, so I'm going to put in, for example, 1 and 1. So if x equals 1, this would be 1 over 1. If x equals 2, this would be 2 over 4. If x equals 3, this would be 3 over 9. Now, if you computed these values, oops, I have an extra equal sign in there, this would be 4 over 16. Now, if you got these values as decimals, this would be 1, this would be 1/2, this is 1/3, so 3 repeating, this is 0.25. You'll notice these values are getting smaller and smaller and smaller. And as you continue to increase your x value, these decimals will continue getting smaller and smaller and smaller, because the difference between a number and that number squared, as that number increases, the difference between those is going to get larger. So this graph here of x over x squared, these y values, as x increases, the y values are getting progressively smaller and smaller and smaller and are going to approach 0. If you put in something like 100 over 100 squared, you'll notice that this decimal is quite small. So what happens when the degree of the top is lower than the degree of the bottom is that you get a horizontal asymptote at y equals 0. And that's because those y values are going to get smaller and smaller and smaller as x increases. Now, if the degree of the top and the degree of the bottom are equal, then what's going to happen, if you notice, if I were to instead use 3x squared over x squared. So those are equal degree. When I plug in these x values now, we would get 3 over 1. We would get, it's very early for this mental math, 12 over 4. Right? We would get, now if you notice already, these are equal to 3, equal to 3. This one's going to be equal to 3 as well, because you've got 3 times 9, which is 27 over 9. So you'll notice that this graph, those y values are all equal to 3. Now, this remains true even if we have, for example, and I'm just using x squared because it's easy to work with, but if I had something like this where the degrees were equal, okay, all of these ratios when I plug in x values are going to be equal to 4 over 5. Now the same is true if I add more terms to this, okay? Even if I add more terms to even just one of the polynomials, as I plug in x values, these y values are still going to generally approach 4 over 5. They won't be exact like they were in the example above, but they are still going to approach that value. So, if the degree of the top is equal to the degree of the bottom, our horizontal asymptote will be at a over b, where a and b are the leading coefficients of our polynomial. So, if we look at some examples of this, so you'll notice I have a note here that says if the degree of the top is larger than the bottom, it leads to an oblique or diagonal asymptote. This is not something that we need to worry about in grade 12 pre-cal. If you're interested in it, you can always look it up. It's kind of neat, but that is a calculus topic. So in these examples, I've just asked you to determine the equations of the horizontal asymptotes. So here, the degree of the top is 1, and the degree of the top is 2. That means that the top is smaller than the bottom, so we have a horizontal asymptote at y equals 0. The second one, the degrees are equal, so the horizontal asymptote will be at a over b. And remember, if there's no value in front, that's a 1, so negative 3 over 1. So the horizontal asymptote will be y equals negative 3. Again here, these are equal, so the horizontal asymptote is at 4 over 12, which is equivalent to 1/3. And in example D, the top has a degree of 1 and the bottom has a degree of 2, meaning there's a horizontal asymptote at y equals 0. Now, if we put this together, on the next 2 pages, I've given you 4 examples where I want you to determine all of these characteristics. So first, determine non-permissible values and determine if it indicates a hole or an asymptote. If it is a hole, you're going to plug in the y value into the simplified equation. And I want to highlight that because that is really important. You're going to plug in that x value into the simplified equation. A hole is a very particular point, so it needs to have an x and a y value. Then determine the equation of horizontal asymptotes, determine x and y intercepts, and determine the domain. So, if we look at our first example, the first thing that I did was I factored everything. So on the top, I factored out the common factor of 4 times x plus 1, and on the bottom, I factored the trinomial. So you'll see here when I'm looking at my factors, I have no common factors. I just have a non-permissible value of 1 and a non-permissible value of negative 2, and those are vertical asymptotes. So for step number 2, it asked if there's a hole, determine the y value. In this case, there is no hole, so I just put not applicable. Tried to keep this nice and organized for you. For step 3, we were looking for the equation of horizontal asymptotes. So if you look at your equation, the degree of the top is smaller than the degree of the bottom. This means there would be a horizontal asymptote at y equals 0. Now, when I've asked you to find your domain, you can remember that your domain is impacted by your non-permissible values. Okay, so those come from the non-permissible values from the beginning when we factored. So this question would have a domain of negative infinity to negative 2, and then negative 2 to 1, and then 1 to infinity. You'll notice I've used round brackets here, and that's because these points, negative 2 and 1, are not included. Okay, so those all come from your non-permissible values. Now I noticed here that I have forgotten to find my x and y intercepts, so I kind of skipped a step. This was actually step 5. Step 4 was finding the x-intercepts. So remember to find your x-intercept. Your x-intercept occurs when y equals 0. But if we notice when y equals 0, this is actually a horizontal asymptote at y equals 0. So this means there will be no x-intercept. Because there's an asymptote at y equals 0, there's not going to be an x-intercept. And if I look at my y-intercept, remember the basics still apply. This is when x equals 0. If I plug that into my equation, oh, I'm off the screen, sorry guys. If I plug that into my equation, and you can use the original equation that you were given, you're going to have 4 times 0 plus 4 over 0 squared plus 0 minus 2. So in this case, we would end up with 8 over negative 2. So your y-intercept is at negative 4. Okay, so that's how we find our x and y intercepts. If we look at question B, again, I started by factoring everything. So you'll notice on the bottom, I have almost a difference of squares. I started by factoring out a negative, and then I was able to split this into a difference of squares. You'll notice here that I have a vertical asymptote at x equals negative 1, because x plus 1 is a factor with nothing else in common, but I have a hole at x equals 1. Now what I mentioned at the beginning and told you to highlight was that to find the y value, you want to substitute in x equals 1 to the simplified equation. So remember in this factored form, x minus 1 and x minus 1 would cancel out. So my simplified equation is just x minus 2 over negative x plus 1. So when looking for the y value of the whole, you're going to plug in x equals 1 to that simplified equation, and you get a value of 1/2. So the whole is at the point 1, 1/2. Now in the next lesson, again, like I said, we will look at actually drawing these, so you'll see what that looks like. Now if we look at our horizontal asymptote, you'll notice the degree of the top is equal to the degree of the bottom. They're both of quadratics. So our horizontal asymptote is equal to the leading coefficient of the top, which is 1, over the leading coefficient of the bottom, which is negative 1. So we would have a horizontal asymptote at y equals negative 1. Again, for some reason, I skipped my x and y intercepts, but I'll talk about domain quickly because it's here. Here, remember, we're going back to our non-permissible values, which are x cannot be negative 1 and x cannot be 1. So in my domain, I'm skipping over negative 1 and I'm skipping over positive 1. Now for your x and y intercept, I'm going to try and squeeze this on the bottom of the page here. Remember, your x-intercept is when y is equal to 0. Now I'm going to use the simplified equation, and I'm going to plug in 0 equals, x minus 2 over negative x plus 1. And what you'll notice here is that my first step would be to try and get x by itself. I could multiply this side by 0. So all that this means is that ultimately the top has to be equal to 0. So 2 equals x would be my x-intercept. And for my y-intercept, I'm just going to plug in x equals 0. So 0 minus 2 over negative 0 plus 1. And here, again, I get negative 2 over negative 1. So my y-intercept is at y equals 2. Okay, so that's the fourth step, and my domain was technically the fifth step. Okay, so those basics of finding your x and y intercepts remain the same. On the back, there's 2 more examples. At this point, I hope that you're kind of getting the routine here and seeing how this works. So here, again, I start by factoring everything. So on the bottom, x plus 2, x minus 2 is a difference of squares. I have no common factors, which means I just have two vertical asymptotes there at 2 and negative 2. There's no whole, so I don't need to worry about that. In this case, the degree of the top is smaller than the degree of the bottom, so the horizontal asymptote is at y equals 0. And again, my domain just skips over my non-permissible values. If you were writing this in the other notation, you could say just x cannot be 2 and negative 2. I guess technically you should write XER such that x cannot be 2 or negative 2. That would be the other notation. I'll let you guys find your x and y intercepts for that. I'm sure you can manage that. And then again on the last one, we've got a difference of squares on the top and bottom. And again, no common factors. So we've got vertical asymptotes at 3 and negative 3, which again links directly to our domain. There's no whole. Our horizontal asymptote, these are equal degree, so a over b, 1 over 1 in this case, so y equals 1 is our horizontal asymptote. And again, you guys can plug in and solve for your x and y intercepts. So that's all the basic characteristics of these graphs. Like I've said a few times, in the next lesson we will actually work on taking this information and putting it on a graph, and I will show you what that looks like.